Ruin theory. So first we'll do this question. An insurance company is a portfolio of 2-year policies. Aggregate annual claims from the portfolio for an exponential distribution with mean 10 follow an exponential distribution. Annual premiums of 15 are payable at the start of the year. Insurer checks for ruin only at the end of the year. Insurer starts with no capital. Calculate the probability the insurer is not ruined by the end of the second year. So we need to see that insurer is not ruined by the end of second year. So first, question 1. Let X be the aggregate claim in year 1 and Y be the aggregate claim in year 2. We require probability of X less than 15 and X plus Y less than 30, or probability of X less than 15 and Y minus 30, Y is less than 30 minus X. Okay, so the probability is all equals to the backslash int X equal to 0 to the power 15 backslash int underscore Y equal to 0 to the power 30 minus X. Okay, backslash lambda square e to the power minus of lambda X e to the power of minus of lambda Y dy dx is equals to backslash of int underscore X equal to 0 to the power 15 backslash lambda whole square e to the power of minus of backslash of lambda X brackets close. Then this is minus 1 divided by lambda e to the power of minus of lambda Y brackets close underscore 0 to the power 30 minus X. Okay, dx. So we are left with this. Next line, backslash of equals to backslash of int underscore 0 to the power 15 backslash of lambda e to the power of minus of lambda X and then minus e to the power of minus lambda X, lambda into 30 minus X, lambda into 30 minus X plus 1 dx. Okay, so next this is equals to backslash of int underscore 0 to the power 15 minus of lambda e to the power minus of 30 lambda plus lambda e to the power minus lambda X dx. Okay, so all this is now equals to alt equals to 30 minus lambda e to the power minus lambda X e to the power minus Just copy this much so that it is easier for us to work. Minus lambda e to the power minus 30 lambda into x minus e to the power minus lambda x underscore 0 to the power 15 is equals to 1 minus lambda e to the power minus 30 lambda into 15. So this is equals to, and minus e to the power minus 15 lambda. Now this is the expression for our values. So the numerical value of lambda now is equals to, since lambda is equals to 0.1, so we have alt equals to 1 minus e to the power 1 minus 0.1 e to the power minus 3 into 15 minus e to the power minus 1.5, which is equals to 0.702. Okay, and next part is CT6 September. Next question which we'll do is September 2010 question 2. Claims on a portfolio of insurance companies follow a compound Poisson process with annual claim rate lambda. Individual claim amounts are independent and follow an exponential distribution with mean mu. Premiums are received continuously and are set using a premium loading of theta. The insurer's surplus is u. Derive an expression with the adjustment coefficient r for this portfolio in terms of mu and theta. So again, next question. Question 2 is equals to backslash of lambda minus CR is equals to lambda m underscore xr. This is the adjustment coefficient. Okay, and then we have C is equals to 1 plus theta into expectation of S is equals to 1 plus theta into lambda into expectation of x, which is equals to 1 plus theta into lambda backslash mu, and m underscore xr is equals to 1 minus backslash of mu r to the power of minus 1. So substituting this in equation 1, we have lambda, okay, this is lambda plus CR, so lambda plus CR or lambda plus 1 plus theta by lambda backslash mu backslash r is equals to lambda into 1 minus mu. This one. Okay, dividing both sides by lambda, we have alt equals to 1 plus theta backslash mu r is equals to 1 minus mu r to the power minus 1, multiplying both sides by 1 minus mu r. So we have alt equals to 1 plus theta backslash mu r into 1 minus mu r is equals to 1. So therefore alt equals to 1 minus mu r plus 1 plus theta backslash of mu r minus of 1 plus theta mu square r square is equal to 1, or alt equals to backslash of mu r into backslash of theta minus 1 plus backslash of theta backslash of mu r is equal to 0. Therefore hence r is equal to 0, or alt equals to r is equals to backslash of theta divided by 1 plus backslash of theta backslash of mu. Okay, since r is positive root, we have r is equals to theta by 1 plus theta into mu. So this is the derivation of the adjustment coefficient. Okay, thank you. Runoff triangles. The cumulative incurred claims for an insurance company for the last 4 accident years are given in the following table. Accident year, development year. It can be assumed that the claims are fully run off after 3 years. The premiums received for each year from 2005 to 2008 are 175, 181, 190 and 196 respectively. Calculate the reserve at the end of the year using the basic chain ladder method and the Born-Horto-Ferguson method. So first is question 1, and we are doing part 1 or part A, say, which is the basic chain ladder method. Okay, so just be consistent on writing everything in caps or everything in small, whatever you're following. So first we'll calculate the development factors. Which is equal to year 0 to year 1, or you can write F01. Okay, so alt equals to either this works or F0 comma 1 also works. Okay, so anything which you feel is comfortable for you, you can write 135 plus 156 plus 130 divided by 96 plus 100 plus 120. This is equals to 1.335443. Then alt equals to, I'm comfortable with writing this. I'm writing this f underscore 12 is equals to 140 plus 160 divided by 136 plus 156, which is equals to 1.027397. Okay, and alt equals to f underscore 2 comma 3 is equals to 168 divided by 140, which is equals to 1.2. So these are the 3 development factors now we have calculated. Now we need to have our table for the basic chain ladder method. If you see, so when you come down, so this is the fully developed chain. If you see, we'll calculate the chain over here, our values. So I'll make a table first. Insert, you can see a table, and how many development years you have. You have 3 development years, and you need, so basically we'll need 5 rows and 4 columns. So just, or you can just draw arbitrarily also. Anything you need, you can add extra. Okay, so there is no hard and fast rule that you will see and you will draw. Anyhow you can draw. Okay, so first is accident year and then is development year. So accident year, here I'm first writing the accident years. Okay, so 2005, 2006, 2007 and 2008. then we have your development years. So what I'll do is I'll just insert one row above, okay, and merge these. So I'll just, if you see there in this layout there is a merge option, if you can see, merge cells. So this is development years, okay, and then I have here which is 0, 1, 2, and obviously since you need an extra row column, so you can again insert columns to the right. So there is this column to the right, okay. No issue, this is not merged, it is understandable that this is the development years, okay. There's no issue. So 96, 136, and I'm just writing the values, 140, then you have 100, 156 and 160, then you have your 120 and 130, and then I have 136, and here I have 168 already given to me. Now I need to calculate this value. So this is equals to nothing but 160 into 1.2, which is equals to 192, okay. 160 into 1.2, which is equals to 192. Then you have here is 130 into 1.027397, which is equals to into 1.2, which is equals to 160.274, and the last one is equals to 136 into 1.335443 into 1.029737 into 1.2, which is equals to, I get is 223.915. okay. So this is how my accident year and development years, so these are the answers. Therefore the final the thing is we need to have the reserve. The reserve is 192 minus 160 plus 160.274 minus 130 plus 223.915 minus 136. So this is equals to 150.189. So this is my reserve for the basic chain ladder method. Now moving on to Born-Haeuter-Ferguson method. If you see, so I'll just make this sure. So this is the BF method. Next is the BF method, the Born-Haeuter-Ferguson method. Okay, now for this again I'll need a table, so insert table, and so I'm drawing extra only. If I need more I'll add. So first for 2008 we are working a bit of so we'll work inverting to 2005. okay, you know we have to work this way because it goes up the other way. So first we have our this f, then we have 1 by 1 minus 1 minus 1 by f, which is the development factors. Then we have the initial liability, and then you have your emerging liability, which is equals to initial ultimate liability into 1 minus 1 by f. Okay, so these are the calculations. So if you see your f for this is equals to 1.64 or 6436. okay, and then for 2007 this is 1.232876. this is 1.2 and this is 1. okay, so this is there. Next is 1 minus 1 by f, so 0.392627, 0.1888, 0.1667, and then this is 0. And initial liability is equals to 188.16, then 182.4, and I'm just writing this calculation. 173 you can do in calculator also, and 168. And the last one is again, if you multiply this, 73.86876, 78, 34.45325, 28.96 and 0. Okay, depending on your loss ratio was 0.96, 168 divided by 175, which is equals to 0.96. Okay, so this is how you can just do, and reserves is therefore 73.87678 plus 34.4525 plus 28.96, which is equals to 137.29. Okay, so this is a born out of Ferguson question, which is a very normal question which can be answered this way only. So there is no issue on this. Okay. Next, moving on to the next year. And next question, which is an inflation adjusted question. Table below shows the incremental claims paid on a portfolio of insurance policies together with an extract from an index of prices. Claims are fully paid at the end of development year 3. So calculate the reserve for unpaid claims using the inflation adjusted chain ladder approach, assuming that the future claims of inflation will be 3% per annum. So question 2, inflation adjusted method, I'll show you. So inflation adjusted method, again first adjusting the incremental data for past inflation to obtain the figures in 2009. So using inflation index, you just need to create a table now. I'm creating extra only, okay, so that it's easier to write my, whether I have to merge cells or anything I can do. So merge cells, this is equals to development year. Year, then this is accident year. Okay, so accident 2006, 2007, 2008, 2009, and the development year is 0, 1, 2 and 3. We need to delete cells, so just delete this column. So just select this column, delete cells, shift cells left, so this is deleted, you don't need this. It's okay if there is a, so I have to demerge and again do this, so it's okay, I'm not doing that. You can leave that like that also, there is no issue. So 103 into, I'll just use already 103 into 111 divided by 100, which is equals to 114.33. Then you have your 32 into 111 by 104, which is equals to 34.154. Then alt equals to, you have 29 into 111 by 109, which is equals to 29.532, and the last one is given to us as 13. Okay, similarly coming down, we have just increasing the size of my column so that it looks a bit better. You don't have to adjust it, I am doing this so that you all can see things properly. Okay, okay, and then 2007 it is 88 into 111 by 104, which is equals to 93.923. Then this is equals to 21 into 111 divided by 109, which is equals to 21.385. Then you have alt equals to, or this is equals to 16. This is there's no value here. Then alt equals to 110 into 111 divided by 109, which is equals to 112.018. Alt equals to, this is equals to 35. Then we have last value is equals to 132. So this is there, and then we have our values, cumulative figures. So cumulative figures at 2009 prices was, so to R, then you just copy. Do not have to always draw the table. You can, if you want, you can draw. It's easier to draw than actually to copy, but you can copy also. I will copy and show you all one. So let's copy this, and we just need to draw a cumulative figure. So then the only thing is you can select the entire thing and erase. Okay, just select the entire thing and delete. So all these values go up: 114.33, then 148.484, then you have your 178.016, then you have 191.016. Coming down, we have the values: 93.923, 115.308, then 131.308. We have 112.018, 147.018, and the last one is 132. So this is there, and then we now calculate the calculation of development factors. So alt equals to f underscore 0, 1 is equals to 148.484 plus 115.308 plus 147.018 divided by 114.33 plus 93.923 plus 112.018 is equals to 1.28270. Then alt equals to f underscore 1, 2 is equals to 178.016 plus 131.308 divided by 148.484 plus 115.308. So this is equals to 1.17261, and alt equals to f underscore 2, 3 is equals to 191.016 divided by 178.016, which is equals to 1.07303. So these are my development factors of projected cumulative prices or figures. Or again, I'll just, my table is already I've copied, so I'll just I'll just select this entire things, whatever I need to write, put a delete. So the values go off, and I'll just need to write the values from here. So 140.897 after multiplication, obviously 184.984, and this is equals to 172.395. Then this is equals to 198.541. This is equals to your 169.316, and this is value is equal to 213.040. Okay, now by subtraction or the projected figures are. These are the incremental figures, so I need the projected figures. So again, I now copy this table, Control V. If this remains 9 point, this becomes 9.589, this becomes 12.589, this is 14.499, then this value becomes 25.376, this value becomes 29.225, and this value becomes 37.316. and this is their projected figures. Adjusted for inflation is Control V. You have this. Not copying that table, I need to write it again. I'll copy this table. This into 1.03 is equal to 9.877. Then you can reduce the size of at least 0 and 1, because not like this, reducing the size. Okay, anyways, just write this. You continue doing. I'll just reduce it when at the last. 12.5789 into 1.03 square. So Alt Shift equals. So this is Control Shift equals 2 is equals to 2 is equals to 13.356. Then you have 14.5 into 1.03. Control Shift equals to 3 is equals to 15.843. Then into also 1.03, which is equals to 26.138, and this is into 1.03. Alt Shift equals to square is equals to 31.005, and this is equals to into 1.03, which is equals to 38.435. Okay, once you get this, then reserves are just the sum of these projected figures, 9.877 plus 26.138 plus 13.356 plus 38.435 plus 31.005 plus 15.843, which is equals to 134.7. So this completes our figures for this also. Thank you.